So again, I'm the architecture professor at College of the Canyons, and one of the things that we've really made a strong transition into is the field of sustainability. And one of the definitions that I like to use in defining sustainability as it relates to pretty much everything is the United Nations definition of sustainability, which is what we see on the screen here. That's meeting the needs of our generation without compromising the ability of future generations to meet their needs as well. That can manifest itself in a lot of ways, in obviously the ability for future generations to have food and water and air and all the basic necessities of life, but also in things like, for instance, in architecture, is how can we build our communities and our buildings and the infrastructure that we need to live in a way that supports future humanity. So one of the biggest impacts to the profession of architecture, over the last 20, 30 years, as we become more aware of things like climate change and global warming, and as we proceed forward with these realities, is how do we deal with greenhouse gas emissions? And so carbon dioxide, or CO2, obviously being a predominant contributor to greenhouse gases. And part of it is understanding, that what we do on a local scale has obviously huge implications across the world. And so if we're going to be emitting greenhouse gases, not just in a let's say a power plant, like we see a smokestack on the left side of the screen, but even individual buildings, often will emit greenhouse gases in maybe how they heat water. So a water heater might combust natural gas, or some other appliance, maybe a heater in a house or something like that. So how can we move away from emitting those gases and instead do what we call electrify a building or decarbonize a building? Because those gases obviously accumulate in the atmosphere and have been the thing that's for many centuries now contributing to the warming of the planet. And so that's something that architects can have an ability to affect. We can also combat global warming in a lot of other really kind of innovative ways. This is a project in Minnesota, and it's actually a museum. It looks kind of like a spaceship, but if we go around to the side of the building, we'll see that it's actually a museum on one of the Great Lakes, and it is naturally daylit. And so it has these gigantic wing elements that kind of open up to let natural light into the building, but they also act to kind of shade the glass from the direct sun so that it doesn't overheat the building too much. And then when the weather's inclement or it's nighttime, these wings are sort of closed up to protect the glass of the building. So it's sort of an animated building, or sort of active kinetic architecture. And obviously naturally daylit spaces are really important, not just for residential buildings, but in the case of commercial buildings. So like this is a building that obviously the public would visit. And so being able to naturally daylight it during the day is a way to reduce the consumption of electricity, which downstream, reduces the need for, creating electricity through burning fossil fuels. The ideal would be that we can generate all the electricity a building like this would need on site. Another big, way that buildings consume electricity and then by default contribute to global warming and climate change is how they get conditioned. We hear the term air conditioner, and we usually think here at least here in California, we think of cooling a building. But in other parts of the country, obviously, you need to do more than cooling. This time of year, obviously, it's starting to get into winter. Winter solstice will be in a couple of weeks, and you need to heat buildings. And so how do we go about doing that without combusting propane or natural gas? And how can we do it through electricity, or maybe no sort of mechanical systems at all? So this project here, which is the Hilton Foundation headquarters in Agoura, California, is naturally ventilated and naturally cooled through a series of kind of ventilation chimneys. So what look like boxy air conditioning units on the roof of the building are actually part of a sort of a chimney where air is allowed to escape out of the building, or in this case, fresh air comes in and it goes down these shafts to the bottom, is cooled in the process. All the heat that's in the air is sucked out through the construction of the chimney. It's a real massive material. It's made of masonry. And that by the time the air is allowed to enter in the building, whether in the office spaces or the lobby, it's cooled off a lot. And then in the lobby or the sort of atrium space, there's high windows or vents that allow hot air that accumulates or that's created in the space to exhaust out. And so there's this sort of natural, what we call a convective loop effect that occurs naturally because of physics. Just simply, we all know that hot air rises. And so by understanding that and providing an opportunity for that hot air to exit the building, we just need to make sure that it's replaced with cooler air. And so the sort of unique system that the architects developed for this project allows that to happen. So simply by opening these windows, that starts that kind of airflow and air conditioning process. And then when we talk about buildings themselves being able to generate electricity, they can obviously do that and should be doing that. And there's a lot of ways to do that. One of the ways that we commonly see is through the use of photovoltaic solar panels, which can be very simple, rigid panels like we might see on a house roof or maybe a commercial building. But they can also be there's some more innovative ways to use photovoltaics. So this project, which is in Switzerland, uses photovoltaics on its roof, but they're sort of disguised or they're integrated into the architecture in a way that you really can't see. And it's using a thin film photovoltaic so that natural daylight is still allowed to enter the building, but you can see on the glass on the image on the right that all those little solar cells or these thin film photovoltaic panels actually help not only generate electricity, but also kind of limit the amount of solar radiation that can come into the building. Now, this project is in a part of Switzerland that's generally pretty cold, and so they can allow a lot more kind of natural light, in from the roof than we would ever really want to do here in Southern California. We would overheat the building, but in other climates, depending on where you are in latitude, what's your relationship to the equator, can change that equation of how much solar radiation you would be getting from the sun hitting the building on the roof or on the walls. So ideally, when we pursue what we call net zero architecture, the idea is that we're, number one, starting with passive solutions so that the building is naturally ventilated and that we've oriented it in ways that helps, at least in Southern California, help keep the building cool. Although if we're in a colder climate, we would orient it in ways that in the wintertime, it actually absorbed heat, and in the summertime was shielded against heat. And then once we've solved that problem, then we think about, okay, how can we now generate electricity to operate the appliances, the equipment, and things that do need to have some means of power. So you can see a naturally daylit building, obviously there's so much nice light, so much ambient light that you really don't need any more lighting other than at nighttime, or if maybe somebody might need a task light for a very specific purpose, they would do that. But again, we're reducing our consumption of electricity so much that we can actually generate all the electrical needs on site. It's an innovative project. This is in Austria. It's a solar tree. So it's a way of incorporating, photovoltaics into more than just a sort of technological solution, but it's something a little more sculptural, a little more artistic. And so I think as our technology, gets more advanced and as we get more comfortable with understanding how to deploy it, we'll see solutions like this that are more integral to our lives. They're not sort of too industrial looking or too ungainly, but can actually be, obviously more attractive addition to our built environment. So what do we teach, and how do we teach architects and interior designers to go about doing the work that they do, the creative work that sort of blends the art and the science of buildings together? So one of the things that we still need to do is sketch. So this project, which we're looking at on the bottom of the screen, is actually Interestingly enough, it's an IMAX theater at a museum complex in Spain. It's in Valencia, Spain, and it's very innovative. It looks like an eye. And so one of the sort of metaphors or one of the concepts that the designer was looking for was that the museum is a sort of eye to the world or to, other realities. And so they wanted to capture that and have the architecture reflect that. So they're conceptual sketches that they did in a sketchbook, or, we have students that do a lot of stuff digitally sketching with like an iPad or something like that. It's a way to get these sort of conceptual ideas, these very raw ideas recorded, and then you start to develop them as you start thinking about things like structure and space planning. Some of the other tools we do drafting. Obviously, this is a very traditional way to draw in our profession. So we do space planning and construction document drawings, and they're just two-dimensional flat drawings, just like we used to do with pencil. Now we obviously do it with computers. But the world is three-dimensional, and so architects and interior designers need to also be working in 3 dimensions. So we use some other programs that allow us to do much more complex geometries and to build things 3-dimensionally, so that we can not only sort of sculpt a building, but understand how we can communicate that to people that are construct it, or to building officials that need to be able to verify that it's code compliant. So we use a variety of different modeling software to do that. And we can get some pretty complex geometries with these programs, even things that may be what we call parametric. So a building like this is the what we call the Gherkin Tower. It's in London, England, and it's a naturally ventilated building. But the exterior skin of the building, or the glass, is pretty complex, as far as the sculpting of it. But it's basically made up of a bunch of diamond-shaped windows or insulated glass panels. And to create that computer model required the design team, have a pretty good understanding of how to use math, and how to use sort of geometry to establish that unique shape. And obviously, it's integrating a lot of really sophisticated structural and mechanical systems in order to accomplish what the building needs to do. Here in Los Angeles, we have some really innovative architecture that also took advantage of 3D modeling. So the Disney Concert Hall, which was designed by Frank Gehry, which we can see on the right, the sort of substructure, or the structural engineering and support system, involved a lot of 3-dimensional modeling to be able to, create these very curvy shapes that we see in the finished building on the right. We also use an even more sophisticated form of digital tool called BIM, or Building Information Modeling, as a way to not only 3-dimensionally model a building, but also that the objects or the parts within the building have an intelligence. So things like doors and windows and roofs and walls aren't just simply 3-dimensional virtual objects, but they have intelligence now. So we know, what that door size is, what's its fire rating, how much does it cost, is it available for a contractor to purchase? So all this background information, this data system is now part of the process that we can build in sort of an intelligence into these models. So they're not just geometric, but they're also data driven. And it allows us to build, go through the building of the building virtually before the contractor actually starts, moving any earth around on site. So we can resolve any conflicts there may be in the building ahead of time, with how all these systems come together, the structure and the mechanical systems. How can we naturally ventilate a building? That's something that we can do in the computer virtually before anything gets constructed, to verify that it's actually going to work. We can also create some obviously very pretty photorealistic renderings. And so our students learn how to create presentation drawings, as part of the model. So the same 3-dimensional model they're using to generate their drawings, that talk about the construction of the building, they can also use that as a way to present to the client and to, try out different materials, different colors, and kind of let their creativity go wild, and to be able to, present that to other people so they can, understand what the concept is. And then we're also really getting heavily into a form of building information modeling that actually does energy simulation. So that's called BEM, or building energy modeling. And so the computer programs allow us to simulate the impact of the sun on the buildings, the natural daylighting characteristics, the flow of air through the buildings, all these sort of sustainability features that we may conceptually incorporate into a building. Now we have a way to actually simulate them to get some data on their effectiveness, and then through an iterative means actually change the design of the building to improve upon those characteristics, so that we can make sure that the building is going to behave the way that we anticipate it to before it actually gets built. And then lastly, one of the sort of innovative things that's come into the profession is 3D printing. Our students use 3D printing as a way to take their virtual digital models and actually create a physical model of it. So something that you can hold, something that you can look at. We also have 3D scanning, so we can then take models that the students may have built and we can digitize that and bring it back into the computer. So you can kind of bounce back and forth between the real and the virtual worlds. And it's also opened up in the actual construction industry an ability to 3D print forms and surfaces. And as this technology expands and gets more sophisticated, we'll start seeing more 3D printed buildings. They've already been doing 3D printed concrete buildings for some time, but they're somewhat crude still, but the technology is improving pretty rapidly. And so we'll be able to take these really complex shapes that students, through their creativity create in the digitally modeling programs, and they can now be constructed using 3D printing as one of the tools. And then lastly, I'm not going to show too much of this video here, but this is a simulation of using virtual reality or augmented reality as a way to do a walkthrough of a design. So as students are creating their architecture digitally, they can now sort of inhabit that space, through the benefit of 3D goggles. And so when we talk about like the metaverse, that's something that we're already working with students actively in, is how can they for visualization and design development purposes, actually go inside their projects. If they see something they don't like, maybe it's just, simply a color of a material, or maybe the space doesn't feel quite right. It's too tight, claustrophobic, or, the proportions are wrong. They have an ability to change that and have a much better sense, a much better way to visualize that through this technology. And so our program here at College of the Canyons, we're one of the larger architecture and interior design programs in the country, and actually one of the largest in the state of California. And so we prepare students for transfer to the Cal Polys and UCLA and the all the upper level universities. And we're actually working on a proposal right now for developing our own bachelor degree in sustainable architecture. So hopefully we see that realized in the next year and a half. Thank you very much.